that. I'm gonna share screen. There's that, and then open that. Okay. So as a comment before we get into it, this Thursday, as you all know, National Turkey Day, very highly celebrated. It's also use math to avoid your family day. So if you have one of those families, we all have that uncle, and you just don't want to sit at the table, you can just be like, I'm sorry, I have to go study sequences and series. And just take your turkey with you. No judging. All right. Okay. So in 11.1, we talked about what a sequence was. Remember, a sequence is a function that if you, where the domain is just your whole numbers, 1, 2, 3, 4, 5. And then a series is when you add the terms of the sequence together. In that section, it was generic to where we didn't have names. We had a couple types of sequences, but in 11.2 and 11.3, we specifically focus on two specific types of sequence. In 11.2, we talk about arithmetic sequences. In an arithmetic sequence, what basically happens is you have your list of numbers as we had before. But what makes it arithmetic is that to get the next number, you keep adding the same number repeatedly, and that number we are adding we call D. So if in a sequence you repeatedly add the same number over and over again, that's what makes it arithmetic. The number D is called the common difference. And the formula for D is written as a sub n plus 1 minus a sub n. And that looks like crazy talk, but all that says in English is to find the common difference, you subtract the second number from the first, or the third number from the second, so on and so forth. So for example, if we had, I'm just making this up, 7, 2, negative 3, negative 8, negative 13, ... Don't get hung up on semantics. What number do we keep adding here?
Negative 5.
Negative 5. So notice if we did 2 minus 7, or negative 3 minus 2, or negative 8 minus negative 3, so on and so forth, we keep getting the same number, and that number is negative 5. So your common difference can be positive, can be negative. It can be 0, but that's very boring. Great. In 11.1, we also talked about finding the general term. Remember, the general term is the term that summarizes all other terms. There weren't any formulas in 11.1 because those were all just generic. They could have been anything. But for 11.2 and 11.3, there are formulas that define the general term, which makes our life a lot easier. The general term of an arithmetic sequence is given by a sub n is equal to a sub 1 plus n minus 1 times d. In order to find the general term, you need two things. You need to know the first term of the sequence, and you need to know the common difference. If you know the first term and the common difference, then you just plug those into the formula and clean it up. So we can do that for this sequence here. We already know that the common difference is -5. What's the first term of this sequence?
The 7.
Excellent. So our general term would be given by the first term, 7, plus the quantity n minus 1. N, remember, acts like your variable here, times the common difference, -5. And then if we distribute that -5 through, and combine like terms, we get -5 plus 12. I'm sorry, -5n plus 12. And we can check it. And the way you check is like what we did on 11.1. If I plug in 1, I do get 7. If I plug in 2, I do get 2. If I plug in 3, I do get -3. So on and so forth. If anything doesn't work, then something went wrong. What format, because remember, sequence is a function, a very specific type of function. What type of function does this look like? How would you classify that? So for instance, instead of a sub n here, and we thought about it as what we did before, this would look like f of x equals -5x plus 12. What type of function is that?
Would that be linear?
It'd be linear. And that's the thing, is an arithmetic general term is always linear. And notice that the slope is the common difference. Always, always. So just keep that in mind if you're ever asked to find the general term. It has to be a linear expression. That won't be true in 11.3. It's just a comment for now. Okay. We can do a bunch of things with this with this general term. Another example of that is, and I'm just making this up, let's suppose this sequence a sub n is arithmetic. And let's suppose that a sub 7 is 12 and a sub, I don't know, 30 is 88. And we're going to find a sub n. This is going to be a preview of what we're going to do in chapter 9. So from before, we know that the general term of an arithmetic sequence is this formula. And by the way, the formulas in this chapter, 11, 1, 2, and 3, are provided for you on the final. You don't have to memorize them. You just have to know how to use them. So that's why we're doing this problem. Well, if we're told that a sub 7 is 12, and that the sequence is arithmetic, that means a sub 7 has to follow this formula, which means it must look like a sub 1 plus something times d. And the reason I'm saying something is we know what n is. by saying a sub 7, that means n is 7. So 7 minus 1 times d. And then being told that a sub 30 is 88, same exact format. It must have the format of a sub 1 plus n is 30 here, minus 1 times d. Well, this is a callback to what you did a while ago in algebra, not necessarily in this class, is you had a system of equations. But instead of x and y, we have a sub 1 and d. The first equation is the same thing as a sub 1 plus 6d equals 12. And the second equation is the same thing as a sub 1 plus 29d equals 88. Oh, this is going to be horrible. You guys don't mind fractions, do you? No, we love them. Okay, great. Then we'll be fine. Thank you for fractions. I do what I can. So, when you were doing this kind of stuff back in, I think this is elementary algebra, you learned two ways to solve. You learned substitution and you learned elimination. This one's set up very nicely for elimination because notice if I subtract the equations, what happens to the a sub 1s?
Cancel out.
They cancel out. So let's subtract these two carefully. So a sub 1 minus a sub 1 gone. 6d minus 29d is negative 23d. And 12 minus 88 is negative 76. All right, so this is horrible, but I'm so sorry. D is going to be what? We would divide both sides by negative 23. So D is a glorious 76 23rds, which I don't think reduces. 23 is prime and doesn't go into 76. Oh well. And then, remember for substitution, you would back substitute. So if a sub 1 plus 6d equals 12, now a sub 1 plus 6 times this wonderful, we're all happy that this number is now in our lives, equals 12. Oh no. I don't know what that is. It's going to look like I'm going to use a calculator. It's because I am. All right, you live over here. What do we need? We need to do 12 minus 6 times 76 over 23. And then convert that to a fraction. Oh, it got worse. Negative 180 over 23. Ugh. So again, to find a general term, you need two things, the first term and the common difference. We just found that, so our a sub n would be the first term plus n minus 1 times d. Oh, and our d is 76 23rds. I get to do this. You can just make a note for it later. If this were on a test, it wouldn't be 23rds, so don't worry too much. And then I'm going to write the word lazy with a smiley face. So then we would do as before. You would distribute, combine like terms, and then a miracle would happen. Miracle. And you'd get the right answer. A sub n is, I don't know what that is, 76 23rds. And oh, what's 76? What's one? Is that negative? 256/23. I think that's right. Negative 180 minus 76. Negative 180 minus 76. I did it. I get a cookie. So chapter 9, we revisit solving systems. This one's not too bad. The one in 11.3 is a little more exciting. Questions so far about what an arithmetic sequence is? Okay. So that's a sequence that's arithmetic. We're still in this section. The rest of the section, now we talk about arithmetic series. And remember, that means we're adding the terms of a sequence. We can only do finite sums. Remember, finite sums was called a partial sum of an arithmetic series. The reason I'm highlighting that is because in 11.3 we will be able to find an infinite sum, which might boggle the mind to how can we possibly add infinitely many numbers. You can under certain conditions, but when it's arithmetic, you cannot find an infinite sum. What will happen is that sum will either grow so big and go towards positive infinity, or it grows negatively so big and it goes towards negative infinity. But finite sum means you stop after a while. Remember, the notation for a finite sum is S sub n, and that tells you where n is the number of terms you're adding. There's a formula. There's actually two formulas for a finite sum. I'll present both. The first one, actually there's no order here. One of them is n over 2 times the quantity a sub 1 plus a sub n. And the second one is n over 2 a sub 1 plus the quantity n minus 1 times d. These are the same formula. As far as when to use which one, sometimes it doesn't matter. But if you know the first term and the last term, the top formula is the best one. If you know the first term and the common difference, the bottom one's the best one. The hardest part will be figuring out the number of terms. So again, n is the number of terms. So for example, if I wanted to find the sum of 1 plus 3 plus 5 plus 7 plus up to 499. Oh my gosh. First off, notice the terms 1, 3, 5, 7, dot, 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 up to 499 is arithmetic, because we keep adding 2. We're starting with the number 1. But also at the same time, we know the first and the last term. So both of these formulas are good to go, and I'll show you both. However, what we don't know immediately is how many terms there are. How many odd numbers are there from 1 to 499? And please don't count them. Oh my gosh. You would need extra toes. How about this? How many numbers are there from 1 to 500?
28.
No. How many numbers are there from 1 to 10? There's 10 numbers. So how many numbers are there from 1 to 500?
To 500. So that means it'll be 499 prime, right?
No. So there's 500 numbers between 1 and 500. Half of them are even. Half of them are odd. Right? So if there's 500 numbers between 1 and 500, then how many odd numbers are there?
It would be 250, right? Because it would be half of 500.
Perfect. There you go. So you might have to do some mental arithmetic, unfortunately, to figure out the number of numbers. Sometimes you can brute force it and count it. Don't do that here. 250 is too big. So you might have to add in stuff that's not there to fill in the gaps and go, oh, it must be half in this case. So our n is 250. If we are using the first formula, your setup would be s sub 250 is equal to 250 over 2 times the first number is 1, the last number is 499. Because we do know the first number and we do know the last number. If you're using the second formula, the setup would be start again with 250 over 2. But now it's 2 times a sub 1. Our a sub 1 is 1. Our n is 250. And the number we keep adding to get the next number is 2. It doesn't matter which one you use, you will get the same answer. I'm using the first one because that's much easier to type into the calculator. 62,500. Let's do another example using these formulas. No, don't delete. I said duplicate. Duplicate. All right, there we go. Let's suppose we had in a stadium, the first row had 25 seats. Every subsequent row had 5 additional seats. My dog is chewing on something. I'm a little concerned. The last row has 125 seats. And the question is, how many total seats? So the first row had 25 seats. The second, each additional row has 5 seats. What are you eating? Don't eat that. That's the carpet. Don't eat the carpet. My God. Oh my God. Why? Everything's fine. Everything's fine. The last row I had 125 seats. And the question is, how many total seats? Boop, boop. So this is arithmetic because we keep adding 5. Both formulas are fine to use. I think the first one's a little bit easier because we know the first number is 25. We know the last number is 125. But what don't we know? We don't know the number of rows, which is what our n is here. Any guesses on how many rows there are?
Would it be 20?
We have a vote for 20. Any other votes? I'm going to add one. Pi. Everybody likes pi. Any other guesses? All right. How do we find out for sure? We got to do some side work. Because I know how you got 20. You did 125 minus 25 divided by 5. Right? Okay. This is where using this formula is going to be very helpful for us. We want to find n so that the last number is 125, the first number is 25, and we keep adding 5. So we could subtract 25 from both sides. We can divide by 5. But what do we get when we solve for n? We don't get 20, we get
21.
21. So in order to get up to 125, we had to add 5 more rows each, 20 more rows each adding 5, but you had to start with your first row. That's why it's 21 and not 20. So our n is 21.
So would the way I did it work if you just added 1 every time?
Yep.
For this kind of sequence? Okay.
Yep. For arithmetic, keyword, for arithmetic.
Okay.
It will not work for the next type. So remember that thing I mentioned at the very, very end, the whole n minus m plus 1 at the very end of the last video? That's where that's where this comes in. Good. So if we put this in the calculator, let's see, 25 plus 25 is 150. Divided by 2 is 75. So whatever 21 times 75 is, oh, I'm not going to do that. I don't want to do that. That's 21 over 2. I'm just going to... Oh, wait, that doesn't make sense. We can't have half a seat. Oh, you know why? Because that should have been 150. So sorry, everyone. There you go. 150. There you go. 1575. Oh. Very good. So side question, if this happened to be a Dave Matthews concert, how many seats would be empty? 1575. It's the same exact question. Same exact answer. Good. Okay. The last part of this, oh boy, oh my gosh, we have to talk faster. The last part of the section is another use of these formulas. So let's do that. This can all go. Let's Suppose we had the sum from k equals 3 to 7 of 5. You know what? Let's go from, I apologize, the sum from k equals 3 to 100. I like that better. 2k plus 1. This is another use of those formulas. First off, we know this is arithmetic. I don't have to say anything because notice this guy is a linear expression. So that hints arithmetic. We're doing a partial sum because we're going from 3 to 100. We're not going 3 to infinity. So because it's arithmetic and it's a partial sum, then these formulas come into play to say, hello. The second equation is actually easier than the first one. Remember, when it's of the format that we have here, the common difference is the slope of the line. So our common difference is 2. Notice the first sum of the first term of the sum starts when k is 3. So if I put in 3 in for k, what's our first number for the sum?
7.
Ooh, in stereo. Good. But now be careful. And this goes back to what Joby was saying earlier. We are going from 3 to 100. How many numbers are there from 3 to 100? And don't say 97. You can subtract the 2, but because we didn't start at 1, you have to add 1 back in. Otherwise, just like the stating one, you're not counting the first row. So it's not 97, it's
98.
98. So that was that whole n minus m plus 1 thing. There are 98 numbers. So exactly the same kind of problem. The only difference is it's now written in summation notation. Boop. 10,388.
Question.
Answer.
I thought it was 98. You put 99, I think, in the calculator.
I did, because notice it says 98 plus 1.
Gotcha.
Is that okay? So instead of putting an extra, thank you for asking. Instead of putting extra parentheses, awesome. All right, that's 11.2. 11.3 mirrors 11.2. And what I mean by that is for 11.2 arithmetic, again, you keep adding the same number over and over. 11.3 is geometric sequences in series. And for geometric, to get the next number, you multiply by a non-zero number. the number you multiply we call R. R is called the common ratio. And the formula says to find it, you divide the second number by the first number. However, there are caveats. The first being that the first number cannot be 0. And I already mentioned the other one, the common ratio can't be 0. Otherwise, you get a whole bunch of zeros. And we don't want that. So, for instance, if we had the sequence 8, I don't know. I have no idea. 4, 2, 1/2, 1/4, 1/8, ... What number do we keep multiplying by?
1/2.
1/2. Good. And again, it has to work for every number shown. If it doesn't, like if instead of 1/8 that was 1/9, it's no longer geometric. It's just a sequence. Okay. And then we have a formula for the general term of a geometric sequence. And that general term is a sub n is equal to a sub 1 times r to the n minus 1 power. So for the sequence in purple here, notice that the first term is r. I'm so sorry. The first term is 8. So our general term would be a sub 1, 8, times the quantity r, in this case a half, raised to the n minus 1. Two comments. Comment number 1. For this one, you technically could rewrite this guy. Like you could write 8 as 2 to the third, and then that becomes 2 to the negative third, and then you can make it one term, blah, blah. Don't do that. Leave it alone. It's totally fine. Keep it in the format a sub 1, r to the n minus 1. Stop. Secondly, for arithmetic, our general term was linear. For geometric, our general term is, where's the variable?
Next one.
In the exponent. Our general term is exponential. Very good. So let's put that to good use. Now, as a comment, if you look at the practice tests, you'll see questions that say, find the general term, part A, part B. And you might also see in the directions, for part B only, use this formula. Please read that carefully. If I'm saying for part B only use this formula, should you use that formula also in part A? No. Please don't do that. That'd be bad. Do students try to do that? Yes. Are they the same students when they were kids that put a round peg in a square hole? Yes. Don't be that guy. So let's do the same thing. Let's find a sub n. If a sub 2 equals, give me a second, 6, and a sub 12 equals, all right, now hold on, this is way too difficult. Why did I do this to myself? Oh no. Oh no. I'm not using a calculator. What are you talking about? What is there? Hold on, I might have to change that 6, everyone. If you have horses, please hold on to them. If you don't have a horse, one will be provided for you. All right. Oh, we can't have that. That's terrible. Hold on, I'm changing it. All right. No. Ah. Oh my God. Oh, I'm so sorry, everyone. It's hard to make pretty numbers. All right, hold on. Okay, scratchy, scratchy, scratch, scratchy, scratchy. I like this one so far. A sub 5 is 48. And A sub 12. Oh, is negative 6144. Don't worry, it's gonna be okay, he says. Okay. So this is another system of equation. This does best mimic what we're going to do in 10.4. So, oh, by the way, this sequence is geometric. I'd have to come out and tell you that. Because it was arithmetic, you couldn't do it, what we're about to do. But we do the same process where we create a system of equations. Since this is geometric, then these guys have to follow this format. So if a sub 5 is 48, then that must look like a sub 1 times r to the n minus 1. Because it's a sub 5, then that n is 5. And if a sub 12 is negative 6144, then that has to look like a sub 1 times r to the 12 minus 1. Which means we have the equations a sub 1 times r to the 4th equals 48. And a sub 1 times r to the 11th equals negative 6144. So again, preview of coming attractions. Your choices are elimination or substitution. We're going to do a substitution this time. And the reason being is elimination implies that you have similar terms in both. We don't have similar terms in both. We only have one term on the left. They're not the same term. We can't just multiply by something easily and subtract them to make things disappear. So instead what we can do is we can take the first equation and we can solve for a sub 1. And if we do that, we get 48 over r to the 4th. Don't worry, I promise this is going to turn out nice. He hopes. And then remember, in substitution, what you do is you go to the other equation, and instead of, in this case, a sub 1, we're going to write 48 over r to the 4th, and then we copy everything else down. Well, this is really r to the 11th over r to the 4th. Remember, when you're dividing two things of the same base, you subtract the exponents. So 11 minus 4 is 7. Now what do we do to solve for r?
Could divide by 48.
We would divide by 48. We get r to the 7th equals negative 128. And how do we get rid of that 7th power? So if that were r to the squared, you would say square root. But if it's a 7th power, you would take a 7th root. I will spoil it for you. You get negative 2. He hopes. No, it's pretty sure. Yeah, I'm pretty sure. Okay, so remember the last step is just like elimination. Now we back substitute. If a sub 1 is equal to 48 over r to the 4th, and we just found r to be negative 2, negative 2 to the 4th is 16. 48 over 16 is 3. So our final answer is a sub 1, 3, times r, negative 2, raised to the n minus 1. So as far as how this is similar, before, to find the general term, we had to find the first term and the common difference when it was arithmetic. To find the general term for geometric, very similar. You find the first term and now the common ratio. So those were our two variables we had to solve for. And we did a system of equations both times. Okay, so that's the sequence part. Questions on the sequence portion of the show. Okay, the series part. There's two parts. There's a formula for a finite, and is a formula for an infinite. The finite formula is S sub n is equal to a sub 1 times the fraction 1 plus r over n over 1, 1 minus r over n over 1 minus r. For the infinite is, I don't know if we have a notation. I think it's S sub infinity. I think that's what we write. Yep. S sub infinity, that's better, is equal to a sub 1 over 1 minus r. I'm going to pull up our last one here. Oh, I apologize. Please write this next to the infinite one. If r has an absolute value of less than 1. There are no restrictions on the finite sum. R can be whatever it wants. But in order to have an infinite sum, you have to be multiplying by a number that's between -1 and 1 exclusively. If not, then the sum will go to infinity or negative infinity, and we don't want that. So a real quick example, we'll compare 8 plus 4 plus 2 plus 1 plus ... plus 1 over 64. And we'll compare that to 8 plus 4 plus 2 plus 1 plus ... So notice the difference is the one on the left is finite because it stops at 1/64th. The one on the right is infinite, goes on forever with a ... at the very end. We have the same difficulty as before. The hardest part is finding n, and notice we only have to worry about that for the finite part. So for this one, let's put in the stuff we know. We know the first term is 8. So that's our a sub 1. And as we discussed before, the thing we keep multiplying by is a half. So that's our r. What we don't know is the number of numbers. Now there are a bunch of ways you can figure out the number of numbers. I'll give you 2. The first way is remembering that because this is geometric, it has to follow, every term has to follow this format. So because of that, we're trying to find n when the first term is 8 and the common ratio is 1/2. And we want this to equal to 1/64th. So notice that this is an exponential equation that's 1 to 1. So you could do this as we did it in section 5.5. Divide both sides by 8, make a common base, set the exponents to be equal. Totally fine, completely legitimate, might take a while. The second way might take 10% less. And the second way is trial and error. And what I mean by that is we want to get to 1/64th. So, okay, I know what that looks like as a decimal. So then you can put this in and then just try numbers in for n. So notice I'm making it look like this common term, the general term, 8 times 1/2 to the n minus 1. So, 1 second, let me do this. So notice here we know n is 1, n is 2, n is 3, n is 4. So our n's got to be a bigger number than 4. So just try a number. Pick one.
$20 maybe.
Sure. So notice I'm purposely keeping in the format n minus 1. We'll talk about why. All right, this number is much smaller than 1/64, which means 20 is too far. So let's try something less. Let's try 10. All right, that was a very lucky guess. I did not mean to do that, but this is what you can do back and forth. Because I kept it in this format, then I know that n must be 10. The reason I'm making a point of that is because if I didn't, and I just did to the 10th power, and that turned out to be correct, then the actual n value is 11, because it has to be n minus 1. So just be careful with that number play there. So now we know our n is 10. So if we put that purple thing into our calculator, please use parentheses. Now that I think about this, this might be an ugly number. It might spit out a decimal. If this were on the test, I'd have to force it to be a friendly fraction or something where the calculator will give you a friendly fraction. I don't think our calculator is going to give us a nice fraction here. Oh my God, it worked. So 8 plus 4 plus 2 plus 1 plus ... plus 1/64 is equal to 1,023 over 64. The good news is that's the hard one. The infinite is much easier, because notice for the infinite all you need is the first term and the common ratio. Well, for us, our first term is 8, and our common ratio is 1/2. We can do this in our heads. 1 minus 1/2 is 1/2. Be careful. 8 divided by 1/2 is the same thing as 8 times 2, because you flip and multiply, and that's 16. So if you added this sum forever, you get 16. That was sort of hinted at us here. Notice when we stopped at the 10th term, we got 15.98, blah, blah, blah. Well, now the rest of the sum fills in the gap and gives us all the way up to 16. So we should have expected our left-hand answer to be smaller than our right-hand answer, because one was finite, one was infinite. Okay. There are definitely some applications of these two, of this formula as well, including using the calculator, using the formula to find a decimal into a fraction when the decimal is repeating. Definitely check those out. Let me know if you have questions. All right, that is 11.3. The good news is, with 15 minutes, we can totally do 9.2, which let me double check. I think that's where we go back to. 9.2, that's correct. 9.2 is actually review. You should have done this in intermediate algebra, which is quite nice. The only bad thing is these are hard to do in the top of my head, so I'm going to cheat. I'm allowed to do that. And I'll pull up a problem from a book that you don't know that I wrote. Let's see, systems, boom. And then I think we'll do that one. That's great. Great. So suppose we had, I should probably write the name. I have no idea what the name is. Oh, it is not going well. Solving systems of equations with 3 variables. All right, I'll write it. Solving systems of equations and 3 variables. The nice thing about this section is it is 100% examples. There's really no theory, which is great. So this is what I had mentioned earlier for 11.3 and 11.2. Your elimination method is the method of choice when you have more than 2 variables, as far as what we're doing in this class. So our job is to find out the x, y, and z values that satisfy all 3 equations at the same time. Let me write this down. So our equations are x plus 3y minus z equals -3. 2x plus y minus 2z equals 4. And 3x plus 4y minus z equals 7. Our job is to find the ordered triple x, y, z. That helps us solve, that will work for every system. This section is very algorithmic. Step 1, step 2, step 3, so on and so forth. And the nice part about this chapter is the majority of the problems can be checked. So you can easily make sure you did it right. Translation, you should not turn in anything wrong because you'll be able to check it on the test, on the midterm, I should say. Okay. Now, even though there's an algorithm and there are steps involved, the way you approach the problem may be different. So there's 7 of us here. We could all do the problem 7 different ways, but we should all get the same answer. So there's that. That's why checking is important. Step 1, and we're going to learn as write the steps as we go, is you want to multiply one or both I'm so sorry. I'll write it that way. Okay. Multiply 1 or 2 equations by a non-zero number so that when added, a variable is eliminated. And I'll read that all again because handwriting is on point. Multiply 1 or 2 equations by a non-zero number so that when added, a variable is eliminated. Okay, there are some tips, suggestions at best. It's easiest to eliminate a variable whose coefficient is 1 or -1. Notice in each equation, at least one of the variables has a coefficient of 1 or -1. So I would suggest let's just eliminate x because the coefficient's a 1 in the first equation. And we have to pick a pair of equations. I'm going to suggest let's pick the first two equations. So what needs to happen is after step 1, we don't want any more x's. For that to happen, because we picked the first two, if this is a positive 2x, then we need this coefficient to be a negative 2x. So what would I multiply that first equation by to make the coefficient of x negative 2?
Negative 1.
Not negative 1, because negative x plus 2x doesn't make it cancel. So we would multiply by
Negative 4.
negative 4. So is negative 4x plus 2x 0x?
So that would be negative 2 if we're trying to get rid of the x's.
Perfect. So we're going to take the first equation and multiply it by negative 2. You have to go all the way through, so that'd be negative 2x minus 6y plus 2z equals positive 6. The second equation we're not going to do anything to, we're just going to copy it down. We do have a bonus here. It's not always going to happen, and you'll see what happens in a second. When we add these two equations, what happens to the x's?
Can cancel out.
Yep. The coefficient of y, negative 6y plus 1y is negative 5y. And here's our bonus. Notice the z's also cancel. That's totally fine. If all three variables canceled, we've got a problem. But if 2 out of the 3 or 1 out of the 3 cancel, that's totally fine. And the constant on the right-hand side is 10. We'll come back to this. We're going to leave that alone. That's our step 1. Step 2 is to pick a different pair of equations. But eliminate the same variable. So we previously picked 1 and 2. So now we are forced to either pick 1 and 3 or 2 and 3. I would suggest 1 and 3, so we keep the coefficient of 1 because that's easiest to eliminate. So if we're looking at the first equation in green and the third equation in green, what should we multiply the first equation by? So when we add it to the third equation, a variable cancels out, namely x cancels out.
The negative 3.
Excellent. Because this is a positive 3, we need the coefficient of x to be negative 3. So multiplying the first equation by negative 3, we would get negative 3x minus 9y plus 3z equals positive 9. And the last equation, we don't change a thing. And I apologize, I'm going to move that over. Oh, who designed this? There we go. Adding them up, notice we get negative 5y plus 2z equals 16. Step 3, we can actually skip, and I'll explain why. Let me write down step 3. Step 3, take the results from steps 1 and 2 and eliminate another variable. The reason our step 3 can be skipped is because in our step 1, we just so happened to get down to one variable. Usually in step 1, you have 2 variables left. In step 2, you have 2 variables left. And then at the end of step 3, you'll have 1 variable left. Well, we were able to bypass that, which is awesome. That saves us a step. So we can go right to step 4, which is solve for the remaining variable. So from step 1, if negative 5y equals 10, what does y equal?
Negative 2.
Excellent. Step 5 is back substitute to find the eliminated variables. Back substitute to find the eliminated variables. So if negative y plus 2z equals 16, that's what we got from step 2. And if y is negative 2, what do we get for z? Excellent. Once you have 2 of the variables solved for, you can go back to the original system to find the third variable. It does not matter which equation you go in, so might as well pick the easiest. Because the coefficient of x is 1 in the first equation, let's use that one. So instead of x plus 3y minus z equals negative 3, we now have x plus 3 times negative 2 minus 3 equals negative 3. What do we get for x?
Six.
Yep. And we tend to write our answers as an ordered triple, x, y, z. Ordered triple from Wendy's. Our x was 6, our y was negative 2, and our z is 3. Comment. Step 6 is check. I always leave that to you. To check it, you have to put 6, negative 2, positive 3 in for the x, y, z in each equation. It has to be true for every single one. If it's not true for one of them, something went wrong. So please check. That's really one example is the whole section. There are some little caveats in terms of having special cases, and that occurs when all of your variables cancel. It's talked about in the book, but the highlight is, I'll do that here. If all of your variables cancel, meaning all the coefficients are 0, there's two possibilities. If you get an equation that is false, because 0 doesn't equal 5, you would say no solution. So all of your variables cancel and you get something false, no solution. If all of your variables cancel and you get something true, then there's infinitely many solutions. The other thing to note, and again, these are in videos, is you might have to turn, for the word problems, you turn English into math and then solve your system. The tip is for those to make sure that you define your variables very well, and then it should go quite smoothly. But yeah, that's it. Congratulations, you survived another week. I hope you have a very